Have you ever considered what might be concealed within a neutron star? This exploration will guide you through one of the universe's most hostile environments, where matter is crushed to an almost unrecognizable state, and the conventional rules of physics start to unravel. Picture a familiar star, a radiant beacon in the night, which, at the conclusion of its life cycle, morphs into something profoundly alien. This final act is a cataclysmic collapse, a cosmic spectacle where a massive star's dying breath condenses energy into a form that defies our imagination. How can an object, no larger than an average city, manage to hold more mass than our own sun? Neutron stars stand as one of the great cosmic puzzles. Born from the titanic detonations of supernovae, their very being poses some of the most profound questions regarding the fabric of our universe. What processes unfold deep within them? How does matter behave under the influence of such crushing gravity? These are the mysteries we will endeavor to solve as we take a deep dive into these celestial marvels. As we investigate more closely, it becomes clear that the allure of neutron stars lies not just in their origins, but also in their complex internal architecture. These objects are composed of distinct layers, each with unique properties. Their structure ranges from an outer crust with a crystal-like lattice to a core that might house the most fundamental particles in existence, showcasing a cosmic ballet between matter and energy. The sheer density of a neutron star is staggering. To offer some perspective, a single spoonful of its substance would weigh as much as a mountain, a concept that truly tests the limits of human comprehension. The gravitational pull on a neutron star presents another phenomenon that defies our everyday understanding of space and time. On its surface, the force of gravity is so powerful that it would instantly obliterate any object that ventured too close. This leads you to wonder what it would feel like to encounter such an extreme force, and how it would warp not only your body, but your very perception of time. The potential answers are as deeply compelling as they are terrifying. Magnetism is another defining feature in the existence of neutron stars. These celestial bodies generate magnetic fields of such incredible strength that they can dominate their cosmic neighborhoods and manipulate surrounding matter. Can you believe that these fields can be billions of times more potent than the one protecting our own planet? This fact is not just remarkable. It prompts us to question how such invisible forces contribute to the overall structure of the universe. Our journey then brings us to pulsars, a specific class of neutron star characterized by rapid rotation and the emission of radiation in precisely timed intervals. While this consistent pulse might appear to be a simple cosmic metronome, it actually serves as a guiding light in the immense darkness of space. We will explore how certain stars evolve into pulsars and what their rhythmic signals can teach us about the fundamental nature of time and motion in the cosmos. Neutron stars are also fundamentally connected to gravitational waves, which are disturbances in the very fabric of spacetime, triggered by cataclysmic celestial events. The analysis of these waves not only deepens our knowledge of neutron stars, but also gives us an unprecedented view into the most powerful occurrences in the universe. What truths about reality itself are being carried to us on these cosmic ripples? The life story of a pulsar is a captivating saga, charting its course from formation to its eventual end. Every phase of this existence is characterized by incredible phenomena that encourage us to contemplate the essence of time and transformation. You might ask what this cosmic life cycle can reveal about our own lives and the role we play in this expansive universe. Naturally, any deep discussion of neutron stars must address the behavior of matter in these extreme states. What exactly is happening at the subatomic level inside these cosmic giants? The potential presence of quarks and gluons challenges our most basic models of matter, urging us to investigate a realm that, while invisible to us, is essential for comprehending the universe's structure. To detect and analyze neutron stars, scientists rely on sophisticated technologies and innovative methods that have transformed the field of astronomy. Instruments from advanced radio telescopes to powerful space observatories provide us with the means to see these celestial bodies in ways previously thought impossible. It is worth considering how these technological advancements have fundamentally reshaped our perception of the cosmos. Finally, we should not ignore the significant mark neutron stars have left on our popular culture, appearing in everything from major motion pictures to classic science fiction novels. The way they are portrayed has ignited the imaginations of countless people. This surely says something profound about our collective fascination with the unknown and our innate drive to venture beyond the familiar confines of Earth. As we lose ourselves in this exploration of the universe of neutron stars, you will find that every answer we uncover only leads to more questions. Science is a journey of perpetual discovery. By seeking to understand these cosmic entities, we are not just learning about the universe, we are also learning more about ourselves and our own position within the grand cosmic scheme. So I invite you to join me on this expedition into the unknown, where each neutron star holds a unique story waiting to be heard. Among the universe's most peculiar and compelling objects are neutron stars. But to truly grasp what a neutron star is, you first need to understand the final moments in the life of a very large star. When such a star depletes its reserves of nuclear fuel, it is destined for a violent end. Rather than simply winking out, it collapses under the immense pressure of its own gravity, triggering a colossal explosion we call a supernova. So, what remains in the aftermath of this cosmic detonation? This is precisely where the neutron star makes its debut. A neutron star is the incredibly dense core left behind after a massive star has gone supernova. To appreciate its density, try to picture a star with several times the mass of our Sun being crushed into a sphere no wider than a city. During this collapse, the pressure becomes so intense that electrons and protons are forced to merge, creating neutrons and giving the star its name. Incredibly, a mere teaspoon of this material would weigh about 1,000,000 tons. It's a truly mind-bending reality, isn't it? Across the vast expanse of the cosmos, stars live out their life cycles, shining with brilliance before ultimately meeting their demise. One of the most captivating final chapters in a massive star's existence involves a process that gives rise to an object known as a neutron star. To grasp how this incredible transformation unfolds, you must first look into the heart of a star during its very last moments. When a star of significant mass depletes its supply of nuclear fuel, it can no longer produce the energy required to resist the inward crush of its own gravity. You can visualize this as a delicate balance. On one side, you have the outward force of nuclear fusion, and on the other, the relentless gravitational pull seeking to collapse the star. Once fusion ceases, that balance is broken, and gravity emerges as the victor in a catastrophic finale. This gravitational collapse is so sudden and immense that it triggers a supernova, a cosmic explosion of unimaginable scale that can briefly outshine entire galaxies. Deep within the core of this blast, where pressures and temperatures reach extreme levels, neutrons are forged. These subatomic particles must struggle to find stability amidst the surrounding chaos, while the star's outer layers are violently cast off into space, revealing a dense remnant that will become the neutron star. The resulting object is astonishingly compact. To put its density into perspective, a single teaspoon of material from a neutron star would have a mass comparable to an elephant on Earth. This extreme compression occurs because gravity forces electrons and protons to merge, creating a sphere composed almost entirely of neutrons. In such an environment, the very nature of matter operates in ways that challenge our everyday experience, governed by a quantum principle called neutron degeneracy pressure, which acts as a final barrier against total collapse. The physical properties of these stars are as remarkable as their origins. A standard neutron star measures only about 20 kilometers in diameter, yet it can contain up to twice the mass of our Sun. Consequently, the gravitational force on its surface is so powerful that it creates conditions approaching the event horizon of a black hole, though these stars have not quite crossed that ultimate threshold. Immediately following its creation, the surface of a neutron star can blaze at temperatures of millions of degrees. While they do cool over cosmic timescales, they stay exceptionally hot, adding to their intrigue. You can picture a sphere of metal so intensely heated it could vaporize nearly any substance on our planet. Furthermore, this intense environment raises fascinating questions about their internal composition, which is believed to consist of distinct layers. The exterior is thought to be a crust, an incredibly dense, solid lattice of ordered neutrons. Beneath this crust lies a region where matter exists in states completely alien to us on Earth. Deeper still, at the star's core, the immense pressure likely forces neutrons into an even more condensed and chaotic state, forming what you might imagine as a sea of subatomic particles. Although direct observation is impossible, scientists use sophisticated methods and experiments to infer the existence of these extreme conditions, where the governing physics often feels more bizarre than fiction. Gravity itself is another captivating feature. If you could somehow stand upon the surface of a neutron star, the gravitational pull would be so overwhelming that even a small leap would be enough to escape into space, yet it would simultaneously crush you with an unbelievable force. This intense gravity also warps the fabric of spacetime, causing a phenomenon known as time dilation, where time flows more slowly near the star compared to locations farther away. Magnetism is also a defining characteristic in the life of these stellar remnants. Neutron stars are capable of generating magnetic fields billions of times more powerful than anything created on Earth, and this magnetism profoundly impacts the star and its cosmic neighborhood. These fields can accelerate charged particles, launching beams of radiation that travel far across space, powerful enough to be detected by our radio telescopes. In some instances, these neutron stars spin at incredible velocities. Think of an ice skater who spins faster by pulling in their arms. A neutron star behaves similarly. As the original star collapses, its rotational speed increases dramatically, which can result in the formation of pulsars, cosmic lighthouses that emit highly regular pulses of radiation. This rotation can be so fast that the star completes a full turn in mere milliseconds. By investigating these extraordinary objects, scientists gain crucial insights into the fundamental forces that shape matter and space. Neutron stars are also indispensable tools for detecting gravitational waves, the ripples in spacetime that offer us information about the most cataclysmic events in the universe. Deep inside a neutron star, matter might even exist in forms we've never observed, with a theorized core composed of a mixture of quarks and gluons, leading us into a realm where the laws of physics are bent in spectacular ways. All of these elements paint a truly fascinating portrait of what neutron stars are and underscore their significance in modern science. These celestial bodies are not merely a display of nature's power. They serve as a gateway to exploring the most profound questions about our universe. As we continue to gaze at these enigmatic objects, we know our exploration is only just beginning, driven by a human curiosity that will forever seek answers. Let's begin by thinking about time. The existence of a neutron star is profoundly different from our own. While a supernova dazzles for just a few days, a neutron star can persist for millions or even billions of years. How can an object of such immense mass and density endure for so long? The key is found in its internal equilibrium and the powerful forces at play within it. As we delve into this, another captivating feature emerges: rotation. Many neutron stars spin at unbelievable rates, sometimes completing hundreds of rotations every second. Picture an ice skater spinning more rapidly as they draw their arms inward. A neutron star undergoes a similar process during its collapse, where the conservation of angular momentum causes its spin to accelerate dramatically, turning it into a detectable source of cosmic radiation. The sequence of events that gives birth to a neutron star serves as a powerful testament to the immense forces shaping the cosmos. A supernova explosion doesn't simply represent the death of a star, it also heralds a new beginning. The heavy elements forged in this cataclysm enrich the surrounding space, providing the raw materials for subsequent generations of stars, planets, and perhaps even life. Take a moment to appreciate the elegance of this cycle. A star's demise provides the very substance for new stars and planetary systems to arise. Every neutron star that comes into being is a reminder that the universe is in a perpetual state of transformation, a cosmic dance that unfolds across immense stretches of time. Investigating the formation of these stars also plunges us into the world of fundamental physics, where we grapple with questions about the essence of matter, gravity, and the forces that govern our reality. Each neutron star is essentially a natural laboratory where the laws of physics are on display under the most extreme conditions imaginable, offering scientists a unique chance to probe the very limits of our knowledge. The creation of a neutron star is merely the start of a thrilling journey into the cosmos. Every new discovery brings us closer, not only to comprehending these remarkable objects, but also to understanding the entire universe itself. After all, every neutron star stands as a monument to cosmic history, an echo of ancient events that continues to reverberate into our present. This process is far more than a simple lesson in astronomy. It's a deep reminder of our own existence and the place we hold in this vast expanse. Reflected in every neutron star are the very forces that led to our being here, compelling us to continue gazing at the sky and to keep asking, what other wonders can we uncover? The story of how neutron stars are formed is an open invitation to explore the unknown, a journey that is truly just getting started. What is it that makes a neutron star so compelling? To grasp the internal workings of these enigmatic celestial bodies, you must first picture how they are born and how their interiors are arranged. A neutron star is the remnant of a supernova explosion, which occurs when a truly massive star collapses under its own immense gravity. But what takes place after its formation? The solution lies within its layered structure. You can think of a neutron star as an onion, but one of a truly cosmic scale. Each layer of this stellar onion possesses distinct properties that make it extraordinary. On the exterior, you have the crust, a region of extreme density composed primarily of atomic nuclei and free-floating electrons. And the fascinating part is that, despite its overwhelming density, the crust is just the outermost shell of what lies within. Beneath the crust, the pressure escalates to such an extent that electrons and protons are forced to combine, forming neutrons, which is precisely how these objects get their name. So what is this inner shell really like? Deeper inside, in the core, the conditions become even more alien. The density is so profound that a single teaspoon of matter from the core would have the same mass as a mountain. Can you even conceive of that? A minuscule amount of material capable of crushing anything we know.
So what is happening within the core? Here, matter behaves in ways that completely defy our everyday intuition. In this incredibly extreme environment, scientists talk about the possible existence of strange matter. As we push against the known boundaries of physics, quarks and gluons, the fundamental particles that make up protons and neutrons, are thought to behave in entirely new ways. In this context, matter can assume forms that we have never witnessed in our world. The internal architecture of a neutron star is captivating, not only due to its composition, but also because it allows us to comprehend how these stars operate on a more fundamental level. For instance, the colossal pressure within the core forces gravity to act in bizarre ways. Can you imagine a location where gravity is so powerful that it actually bends the fabric of space and time? That is precisely what occurs inside a neutron star. Furthermore, the core temperature can soar to millions of degrees, fostering extreme conditions where nuclear reactions can take place. These reactions within a neutron star can directly influence the synthesis of new elements, thus contributing to the creation of the very matter that forms our world. The crust, while being the outermost layer, also has a vital role to play. It can be the stage for phenomena like starquakes, which are massive discharges of energy resulting from shifts in the star's internal structure, making it a key region for observation. Ultimately, the density and pressure inside these objects are so extreme that the physics you are familiar with no longer consistently applies, which raises compelling questions about the laws of nature. Neutron stars function as cosmic laboratories, enabling us to test our theories about matter and energy in states we cannot reproduce on Earth. By studying their internal structure, we also deepen our understanding of other astrophysical marvels, like black holes, opening up a new universe of possibilities in our quest for cosmic answers. Have you ever paused to consider the true power of gravity? Here on Earth, it's a constant force we barely notice, keeping our feet on the ground. But what happens when you amplify that force to an unimaginable degree, to a place where gravity itself warps our very understanding of reality? This brings us to neutron stars, some of the most mysterious and extreme objects in the universe, where the force of gravity reaches its most profound levels. Investigating neutron stars is much more than an exercise in scientific curiosity. It offers us vital clues about the ultimate fate of stars and the overarching evolution of the cosmos. These genuine titans of the universe possess a density so astonishing it almost defies belief. To give you a sense of this, a single teaspoon of material from a neutron star would weigh as much as an elephant. This fact alone makes these stellar remnants both endlessly fascinating and incredibly difficult to comprehend. The concept of a neutron star's density radically challenges our intuitive grasp of the physical world, forcing us to reevaluate what we think we know about matter and gravity. For comparison, our planet Earth has an average density of about 5 grams per cubic centimeter. A neutron star, however, has a density of approximately 1 billion grams per cubic centimeter. This means the matter within it is compressed so intensely that atoms can no longer exist in their familiar form. You are probably asking yourself how such an extreme compression of matter is even possible. The answer lies within the overwhelming gravitational force at the core of these objects. When a very large star reaches the end of its life, its core collapses under its own colossal weight. This atomic collision forges a completely new state of matter, as electrons and protons are fused together to form neutrons, giving birth to what we call a neutron star. This process is a true spectacle of nature, where gravity dictates the extraordinary outcome. In this unique state, it is believed that neutrons are packed so tightly that they behave in ways we can never observe on Earth. This gives rise to bizarre phenomena, such as degenerate matter, a condition where the familiar laws of physics no longer apply in the conventional sense, opening a door to the world of quantum mechanics. A neutron star is far denser than any ordinary planet or star, representing a state of matter on the boundary between a standard star and a black hole, which makes it a thrilling and active area of research in astrophysics. The extreme density of these stellar objects is not just an abstract idea. It helps us understand how matter behaves under the most severe conditions, which has implications for fields like materials physics and cosmology. In essence, these stars are natural laboratories for testing physical theories that are impossible to replicate on Earth. Furthermore, the incredible density of neutron stars influences the creation of new elements. When two of these objects collide, the event produces powerful gamma-ray bursts and is thought to be responsible for forging many of the heavy elements found throughout space. This means the very matter that constitutes our world may have originated in the cataclysmic merger of neutron stars, providing a direct link between these exotic objects and our own existence. By studying these phenomena, we gain a deeper appreciation for how stars are born, how they live, and how they ultimately die. Each new discovery about these objects brings us one step closer to understanding our own place in the universe. In the end, a neutron star's internal structure is a microcosm of amazing and complex forces, where each layer, from the outer crust to the enigmatic core, offers a fresh perspective on matter and energy. As we continue to explore the cosmos, neutron stars will remain beacons of knowledge in the vast darkness of space, illuminating pathways we have yet to travel. So the next time you look up at the night sky and marvel at the stars, remember that some of them are not just points of light. They are reminders that the universe is far stranger and more wonderful than we can possibly imagine, holding countless surprises that await our discovery. Consider for a moment that you could take a piece of matter from a neutron star, no bigger than a sugar cube. That tiny fragment would carry the same mass as an elephant. It's a startling thought, isn't it? This is a direct demonstration of gravity's immense power. The gravitational force within a neutron star is so overwhelming that it crushes all matter, compressing it to densities that are nearly impossible to comprehend. Gravity's influence extends beyond just matter. It also profoundly impacts the flow of time. In the immediate vicinity of a neutron star, time itself behaves differently, slowing down considerably. If you were positioned there, a single second passing for you could feel like an entire minute for an observer back on Earth. The fact that gravity can warp our very perception of time is a truly fascinating concept. Moreover, the intense gravity of these stars alters the path of light itself. Light, which we understand to travel at a constant speed, is forced to bend as it passes through such a strong gravitational field. Think of it like a ball rolling across a field, its path curving as it encounters a hill. In the case of a neutron star, light attempting to escape its pull is bent so severely that it creates an effect where the star seems to hide light, a phenomenon reminiscent of an event horizon. The gravitational pull of a neutron star can also give rise to accretion disks formed from nearby material.
These are swirling vortices of gas and dust that orbit the star, relentlessly drawn in by its immense gravity. This process is not only visually spectacular, but also releases staggering amounts of energy, generating radiation that we can detect all the way from Earth, offering us a distant window into the activity surrounding these cosmic objects.
Neutron stars are often born from the cataclysmic explosions of supernovae, where gravity plays the central, decisive role. When a massive star depletes its nuclear fuel, its core collapses under its own gravitational weight, forging a neutron star. This transformational event unleashes a colossal burst of energy into the cosmos, and it is this very energy that enables us to identify and study these extraordinary celestial bodies.
What might it be like to actually journey to a neutron star? Such an experience would be a mixture of terror and exhilaration. The gravitational force is so potent that any object, including an astronaut, would be instantly crushed beyond recognition. The behavior of matter in this extreme environment is so alien to our everyday experience that it compels us to re-examine the very laws of physics as we currently understand them. Could anyone possibly survive in such a place? The unfortunate but definitive answer is no. Even so, despite their hostile nature, neutron stars provide an unparalleled opportunity to witness phenomena that are impossible to replicate here on Earth. They permit us to probe the absolute limits of physics and achieve a deeper understanding of the universe's mechanics. By investigating the gravity of these stars, we not only uncover the secrets of their own existence, but also gain fundamental insights into the nature of gravity itself. As our comprehension of neutron star gravity deepens, we find ourselves facing intriguing new questions about the cosmos. What other secrets are concealed in these extreme corners of space? How does our knowledge of their gravity connect with the other fundamental forces of nature? Each discovery seems to open the door to more questions, propelling an unending cycle of exploration. It's also possible that the relationship between gravity and matter in these stars could lead us to reconsider the very fabric of time and space. Could it be that gravity, in its most extreme form, affects other aspects of the universe that we have yet to grasp? Science is in a constant state of evolution, and every new finding brings us a step closer to solving these profound mysteries. With each advance in the study of neutron stars, new horizons of understanding appear before us. The gravity of these celestial objects is more than just a scientific point of interest. It helps us to chart the universe and comprehend our own position within it. It serves as a powerful reminder that while we may be small in the face of the cosmos, every discovery brings us nearer to unraveling the great puzzle that surrounds us. Neutron stars stand as a testament to how much there is still left to explore and learn about our universe. Every time you gaze at the night sky, you are not just looking at stars, but at phenomena that actively challenge our perception of reality. The gravity of neutron stars is merely one of the countless wonders that await us on our continuing journey of cosmic discovery. Did you realize that neutron stars are counted among the most enigmatic and captivating objects in the entire universe? Possessing unbelievable density and incredibly powerful magnetic fields, these stellar remnants act as cosmic lighthouses, beckoning us to explore the frontiers of physics. But what exactly constitutes a neutron star's magnetic field, and what makes it so extraordinarily powerful? To begin with, the magnetic field of a neutron star is intrinsically linked to its formation process. At the end of its life cycle, a giant star collapses under its own immense gravitational force. This collapse not only squeezes matter into unimaginable densities, but also dramatically magnifies the star's original magnetic field. Picture squeezing a simple magnet into a much smaller volume.
its magnetic field would become intensely concentrated, which is precisely what occurs with a neutron star. The sheer force of these magnetic fields is astounding, capable of reaching intensities millions of times greater than that of Earth's own magnetic field. To offer some perspective, if you could somehow stand on the surface of a neutron star, the magnetic field would be so intense that it would violently tear apart any object that ventured too close, no matter how durable its material. The magnetic field of a neutron star isn't simply an object of scientific curiosity. It produces real and spectacular consequences. For instance, it can accelerate charged particles to nearly the speed of light, and this process generates powerful electromagnetic radiation, often in the form of X-rays that our instruments on Earth can detect. Using telescopes that observe across various wavelengths, astronomers are able to capture these signals, confirming the existence and activity of these immense magnetic fields from light years away. The magnetic field of a neutron star is more than just a measure of its strength. It's intricately connected to the behavior of matter under the most extreme conditions imaginable. Deep within the core of a neutron star, the laws of physics operate in ways that challenge our everyday intuition, compelling familiar particles like protons and electrons to merge and form neutrons. This exotic soup of particles forges an environment where the forces of gravity and magnetism are woven together in profoundly complex patterns. Did you realize that certain neutron stars possess magnetic fields so immense they earn the special designation of magnetars? These objects represent the most extreme variants of neutron stars, with magnetic fields so powerful they can unleash colossal bursts of energy as gamma rays. For a fleeting moment, these events can make a magnetar one of the most luminous objects in the entire universe at specific wavelengths, releasing an amount of energy capable of lighting up a massive section of the cosmos in an instant. Now, let's consider for a moment how these stellar remnants behave as they move through space. Thanks to their rapid spin and potent magnetic fields, some neutron stars project beams of radiation that sweep across the cosmos, much like the beacon of a lighthouse. This is the phenomenon we identify as a pulsar. When one of these rotating beams happens to be aimed in our direction, we can observe it from Earth as a series of regular, pulsing signals. This interplay between a star's rotation and its magnetic field serves as a stunning illustration of how different cosmic forces can interact in extraordinary ways. It is truly remarkable to consider that, as they spin, pulsars can emit signals with a precision that rivals atomic clocks. This not only equips us with an invaluable tool for exploring the universe, but also enhances our comprehension of the fundamental properties of time and space itself. In a way, you could think of these pulses as the very heartbeat of the cosmos, establishing a steady rhythm for the universe. Moreover, the magnetic field of a neutron star holds significant implications for the observation of gravitational waves. When two of these dense objects collide, the event generates gravitational waves that ripple across the fabric of the universe. You can imagine these waves as echoes from cataclysmic events, carrying stories about the birth of stars and the ongoing evolution of the cosmos. So, whenever you hear about the detection of gravitational waves, you are essentially listening to the whisper of magnetism and gravity, locked in an intricate cosmic dance. As we delve further into the study of these powerful stellar objects, it becomes clear that their magnetic field is not merely an isolated characteristic, but is fundamentally linked to the very structure of the universe. Investigating these forces helps us to piece together the great mysteries of matter, energy, and time. On a more reflective note, contemplating the magnetic field of a neutron star can lead you to ponder your own place in it all. If such entities can wield this level of power and influence, what does that suggest about our own significance on a cosmic scale? Ultimately, the true essence of a neutron star's magnetic field may not just be in its physical properties, but in how it connects you to the cosmos. So, the next time you gaze up at the stars, remember that there is so much more happening than what you can see. A neutron star's magnetic field is just one of the countless wonders awaiting discovery, reminding us that even though we are small, our curiosity is what compels us to explore and comprehend our place in this vast universe. Neutron stars are undeniably among the most captivating objects known to exist, and their swift rotation adds another layer to the enigma they present. But what is the real significance of a neutron star spinning at such incredible velocities? To grasp this, it helps to first picture a common object, a spinning top. Think about how a top becomes more stable the faster it rotates. This very same principle applies to neutron stars, whose high-speed spin grants them an astonishing degree of stability. Just how fast can these stellar cores rotate? Some are capable of completing a full spin in a matter of milliseconds, a duration shorter than the blink of an eye. Try to imagine that, a star turning so quickly that if you were to observe it up close, it would look like a cosmic lighthouse, flashing beams of light and radiation at precise intervals. This effect is precisely what defines a pulsar, and it stands as one of the most fascinating outcomes of a rapidly spinning neutron star. The origin of this breathtaking rotation lies in a fundamental law of physics known as the conservation of angular momentum, which you can see demonstrated by an ice skater. When a skater pulls their arms in tightly during a spin, their rotational speed dramatically increases. In a similar fashion, when a giant star collapses at the end of its life in a supernova explosion, its core is crushed into an incredibly dense object. This compression forces the resulting neutron star to spin at a phenomenal rate, accelerating its rotation in a truly spectacular transformation. The spin of these stars is not only incredibly fast, but also generates extraordinary effects in the space around them. As they rotate, their immense magnetic fields are amplified and can become aligned in a way that creates focused beams of radiation shooting out into space. When these beams of energy sweep past Earth, we are able to detect them as a sequence of pulses, which is how the name pulsar came to be. This means a neutron star can be thousands of light years away, yet its presence can be seen from our planet whenever its beacon is pointed toward us. Think of each pulse we detect as a single beat from a cosmic heart, with every beat carrying vital information about the star, its rotational speed, and its magnetic properties. Consequently, whenever astronomers locate a new pulsar, they effectively become cosmic detectives, tasked with decoding the secrets concealed within that spinning stellar remnant. However, not all pulsars are identical. Some rotate at a leisurely pace, while others spin with extreme velocity. The key to telling them apart lies in the timing of their pulses, as the fastest pulsars can emit signals multiple times per second, whereas the slowest may have several seconds between each pulse, allowing us to categorize and better understand their nature. The spin of a neutron star presents some truly captivating consequences for the field of physics. By observing these pulsars, you can see how researchers have been able to put theories of relativity to the test, investigating the principles of gravity in the most severe environments imaginable. For instance, the immense gravitational pull of a neutron star warps the flow of time itself, causing it to proceed at a slower rate than we experience here on Earth, a concept that is as perplexing as it is incredible. The rapid spin of these celestial bodies also gives rise to extraordinary events on their surfaces. While a neutron star possesses a solid outer layer, its core is subjected to such intense pressures that matter exists in states that defy our current comprehension. This fusion of extreme density and swift rotation can produce formations beyond anything you might envision. With every new observation,
astronomers move closer to grasping the mechanics of these amazing cosmic objects, treating each discovered pulsar as another vital piece of a grand puzzle that reveals secrets about the stars and the universe itself. While conversations about neutron stars often focus on their staggering density, their rapid rotation is a feature you shouldn't overlook. The velocity of their spin, combined with their environmental interactions, is essential for comprehending their place in the cosmos and their effect on other celestial events. As our technology and research methods improve, so does our knowledge of these pulsars, continually unveiling a universe brimming with secrets and wonders. So, the next time you think of a pulsar whirling through space, consider that every signal it emits is part of an incredible narrative yet to be fully told. You can think of neutron stars as lighthouses piercing the cosmic darkness, but their significance extends far beyond simply lighting up the universe. They are instrumental in detecting gravitational waves. To grasp the importance of these waves, you must first picture spacetime as a vast, flexible sheet, much like a trampoline. A massive object, such as a star, creates an indentation on this surface. If that star then undergoes a violent event, like a supernova, it doesn't just warp the sheet. It sends out ripples that propagate across it. These are gravitational waves, traveling at the speed of light, generated by cataclysmic events like the collision of two neutron stars. The moment scientists first directly observed gravitational waves marked a turning point in history. Imagine teams of researchers holding their breath as they monitored instruments for the faintest tremor that would validate a prediction Albert Einstein made over 100 years prior. Then, a single alert, a signal that fundamentally altered our perception of the cosmos. It was akin to discerning a whisper from across a crowded stadium, faint yet profoundly meaningful. Colliding neutron stars are particularly potent sources of these gravitational waves. Such mergers don't just generate ripples in spacetime, they unleash a staggering quantity of energy, comparable to thousands of supernovae combined. The next time you hear about such a merger, you should envision a celestial performance where space and time themselves engage in a powerful, wave-like dance. What does this mean for the field of astrophysics? Detecting gravitational waves has armed us with an entirely new method for observing the cosmos. It enables scientists to witness events that were once completely hidden from conventional telescopes. You could say it's like we've developed a new sense, one that lets us hear the symphony of the universe. This new perspective enhances our understanding of neutron star behavior and sheds light on the fundamental properties of gravity and its interaction with matter. This interplay between gravitational waves and neutron stars also raises fascinating possibilities. Could observing these mergers provide the insights needed to finally comprehend dark matter and dark energy? With each detection, we inch closer to solving the cosmos's deepest puzzles. But this field extends beyond pure theory. You might be surprised by the potential for practical applications. By studying these extreme cosmic events, we might unlock principles that could eventually shape terrestrial technology, perhaps even learning from stellar explosions how to develop novel energy sources that could transform our world. The study of neutron stars and gravitational waves inevitably leads you to ponder your own existence within a universe of constant change. Looking up at the night sky serves as a powerful reminder that you are not merely an observer, but an active part of this magnificent cosmic drama. The philosophical ramifications are profound, as the intersection of quantum physics and relativity in this context forces us to re-examine our very concept of reality. It provokes questions about whether time is linear or cyclical, and if the universe is finite or part of an eternal cycle of birth and decay. In this quest, neutron stars serve as cosmic keys, helping us probe these fundamental inquiries.
With every technological leap, our capacity to detect and analyze gravitational waves grows more sophisticated. Advanced facilities like the LIGO interferometer and the Virgo Observatory are bringing us nearer to comprehending the full structure of the universe, far beyond just neutron stars. It's impossible to predict what discoveries lie just over the horizon. Ultimately, you can think of gravitational waves as the residual echo of the cosmos, a faint whisper from the monumental events that have sculpted the reality we inhabit today. Whenever you consider neutron stars and their relationship with these cosmic waves, you should realize we are tuning into the symphony of the universe. Every single detection serves as a confirmation that an immense ocean of space still holds countless discoveries and lessons for us to uncover. The existence of a pulsar is a remarkable saga that originates from the spectacular death of a colossal star. After a massive star consumes all its nuclear fuel, its core undergoes a dramatic collapse, triggering a supernova explosion. The material left behind doesn't simply scatter into the void. Instead, it condenses into a neutron star, an object of incredible density that can sometimes evolve into a pulsar. During this stage of its life, the neutron star spins at incredible speeds, occasionally reaching up to 1,000 rotations per second. This breathtaking spin is what transforms certain neutron stars into pulsars, a unique subclass of these stellar remnants. The central question, of course, is how exactly they operate. To understand their function, you can picture a lighthouse adrift in the cosmos. As this cosmic lighthouse spins, its beam of light sweeps across space, becoming visible to you only when it points in your direction. A pulsar operates on a similar principle, projecting beams of radiation at precise intervals. When our planet Earth intersects the path of one of these beams, we register them as periodic pulses of light or other radiation. The origin of these pulses is genuinely fascinating, stemming from the interplay between the star's swift rotation and its immensely powerful magnetic field. Much like a spinning top, centrifugal force flings matter outward, while the magnetic field funnels charged particles into focused streams. This dynamic process generates the beams of radiation that travel through space, and we perceive them as a celestial rhythm when they align with our world. Pulsars are remarkable not just for their rhythmic emissions, but also for their phenomenal consistency. If you can imagine a timepiece that is never fast or slow, you can appreciate their value. Some pulsars exhibit such astonishing regularity that they function as cosmic metronomes, enabling us to measure time with breathtaking precision. This capability has profound consequences for astrophysics, as studying these universal clocks allows us to investigate physics in extreme environments and observe how matter behaves under conditions we can scarcely comprehend. The life of a pulsar, however, does not last forever, as the energy it radiates gradually wanes over time. You can think of it like a flashlight with dying batteries. A pulsar's emissions eventually grow faint and cease. Before reaching this final stage, these celestial objects can exist for millions of years, continuously broadcasting their signals across the cosmos as a persistent reminder of their presence. These objects also have a significant effect on their immediate cosmic neighborhood. Many pulsars are enveloped by interstellar material or the debris of other stars. As they spin, their powerful gravity can draw this material inward, forming structures known as accretion disks. In a sort of cosmic ballet, this captured material heats up and radiates energy across various wavelengths, allowing the pulsar to light up its surroundings and act as a powerful beacon in the darkness of space. The journey of a pulsar is ultimately one that leads to its own end. As its energy reserves are exhausted, its rate of rotation decelerates and its magnetic field diminishes. This decline concludes in what is referred to as the death of a pulsar, at which point it no longer emits pulses and transforms into a cold, inactive object. Yet its influence persists, as the waves it sent out continue their voyage across the universe, carrying the chronicle of its existence with them. Pulsars have been fundamentally important to the advancement of science. During the 1970s, the identification of a pulsar within a binary neutron star system provided scientists with a new framework for understanding both relativity and quantum physics. This breakthrough created new pathways for exploring gravity and the nature of time, demonstrating that even the densest, most compact objects can offer profound insights into the workings of the universe. So, what essential truths do pulsars reveal about the cosmos we inhabit? They teach us that the end of a star's life is not a conclusion, but a transformation into something entirely new. In the grand cosmic cycle of creation and destruction, they show us that every star has a purpose, even in its final moments. Examining pulsars also deepens our knowledge of how matter functions under the most extreme pressures and densities imaginable. This research compels us to contemplate the behavior of matter when it is subjected to forces beyond our everyday experience. It challenges our established understanding of physics and encourages us to speculate on how the universe might evolve in the distant future. When you reflect on the life cycle of a pulsar, it is easy to feel a sense of awe at the sheer scale of the cosmos. Each of these celestial bodies serves as a source of knowledge, a monument to the history of the universe, and a testament to the intricate beauty of stellar evolution. Pulsars are more than just subjects of scientific inquiry. They are the narrators of cosmic epics, and every signal they transmit is like a beat of the universal heart. Consequently, when we gaze at the night sky and ponder these neutron stars, we are seeing more than just distant light. We are looking into a mirror of our own cosmic journey. The existence of a pulsar is ultimately a reflection of humanity's ongoing quest to find its own place within the vast and enigmatic universe we call home. At the very core of neutron stars lies an astonishing concept known as strange matter. But what is this substance, and what makes it such a source of intense scientific interest? Strange matter is a state of being that operates under a completely different set of rules than the matter you encounter in daily life. If you have ever tried to conceive of a substance with unimaginable density and bizarre properties, you are beginning to grasp the idea. First, you need to consider the basic composition of matter. In our world, everything you see is built from atoms, which themselves are composed of protons, neutrons, and electrons. Within a neutron star, however, the conditions are so severe that atoms are torn apart, and matter is forced into an entirely new and different state of existence. You can visualize a neutron star as a place where gravity is so overwhelmingly strong that it crushes matter into itself, which is precisely how these objects come to be. You might think of a neutron star as a cosmic titan that has endured a universe-altering collapse. Deep inside its core, subjected to pressures beyond all imagination, protons and electrons are squeezed together until they merge, forming a dense sea of neutrons. This is where the magic truly unfolds. The density becomes so extreme that a small cube of material from a neutron star would have more mass than an entire mountain. It's a concept that is difficult to grasp, But it leads us to question what lies deeper. Inside the neutrons themselves, you find the subatomic particles known as quarks and gluons, which are the essential building blocks of all matter. Quarks can be thought of as the primary components of neutrons and protons, while gluons represent the powerful forces that bind them. Within a neutron star, the immense pressure can cause these quarks to break their bonds and create a state known as quark matter. Imagine the ingredients of a complex recipe suddenly escaping their container and beginning to move about freely. This phenomenon has profound implications for our comprehension of the universe, as neutron stars serve as natural laboratories. In these cosmic settings, physics operates in ways we could never hope to reproduce here on Earth, offering scientists a window into how matter behaves under the most severe conditions imaginable.
Imagine you had the chance to witness a kitchen where the fundamental laws of cooking were entirely different, yielding bizarre and unexpected results. In this same spirit, the potential existence of strange matter introduces some truly captivating possibilities. Could it be possible for life forms to exist that are based on this exotic substance? Or could there be planets in some distant corner of the cosmos constructed entirely from strange matter? The very thought of alien life forms we can't even conceive of compels us to reevaluate everything we know about biology and chemistry.
Moreover, the investigation into strange matter extends beyond mere theory and into the realm of practical application. For instance, a deeper understanding of how this substance behaves could empower scientists to pioneer new technologies in fields like energy production or advanced computing. It's akin to learning from a wise, ancient master who possesses secrets capable of transforming our entire way of life. Neutron stars and strange matter are locked in a cosmic ballet that has captivated physicists and astronomers for decades. The quest to understand these celestial objects not only illuminates their own nature, but also forces us to consider our own place within the vastness of the cosmos. Every new insight gained about strange matter brings us one step closer to solving the great cosmic puzzle. As our exploration of neutron stars deepens, we find ourselves confronting more questions than answers. For example, what is the fate of strange matter when a neutron star finally collapses and transitions into a black hole? This process remains one of the great unsolved mysteries in astrophysics and is a very active area of current research. The implications of strange matter also reach far beyond the confines of neutron stars themselves. Some scientists theorize that this exotic material might be present inside certain planets, or could even be a component of dark matter, the enigmatic substance that constitutes the majority of the universe's mass. With every fresh discovery, the frontiers of our knowledge are pushed further, challenging our most fundamental understanding of matter and energy. Strange matter truly represents a fascinating enigma residing at the very core of these incredible stellar remnants. Throughout this cosmic journey, we have explored the wonders that neutron stars present and how they expand our comprehension of the universe. It is human curiosity that will forever propel us toward seeking answers to these profound questions. And when it comes to strange matter, there is still an immense amount left to uncover. So, the next time you gaze up at the night sky, remember that hidden within each of those distant neutron stars is a universe of mysteries just waiting to be revealed. Neutron stars are undeniably among the most mesmerizing objects in the cosmos, but how can we be certain they actually exist? The answer isn't straightforward and requires a journey into the world of astronomical observation. The search for these stars is much like a celestial game of hide-and-seek, compelling astronomers to employ clever instruments to locate these elusive bodies within the immense expanse of space and time. One of the most effective techniques for detecting neutron stars involves X-ray observations. Picture yourself attempting to locate a tiny light in a vast, dark expanse by using a bright flare. Because of their extreme temperatures and densities, neutron stars radiate immense amounts of X-rays, essentially acting as beacons in the cosmic night. When a neutron star is part of a binary system and siphons material from its partner star, that material heats up intensely, emitting X-rays that allow scientists to pinpoint its location. Radio astronomy is another vital tool in the hunt for these exotic stars. In some cases, a neutron star spins at such a tremendous speed that it emits beams of radio waves at precise, regular intervals, much like a lighthouse sweeping its beam across the sea. These objects, which we call pulsars, transmit signals that can be captured by radio telescopes on our planet. It is comparable to tuning into a faint radio station through an overwhelming amount of static. With the right equipment, astronomers can discern the unique rhythm of a pulsar from thousands of light years away. An equally compelling method is the detection of gravitational waves. When two neutron stars spiral into each other and collide, they produce ripples in the fabric of space-time itself. Advanced detectors, such as the Laser Interferometer Gravitational Wave Observatory, or LIGO, are sensitive enough to hear these waves, similar to feeling the vibrations from a distant drum. This technique not only verifies the existence of neutron stars, but also gives us a direct view into some of the most powerful events the universe has to offer. High-energy telescopes also play a significant role by detecting gamma-ray bursts, which are the most powerful form of light known. These bursts are frequently linked to the cataclysmic deaths of massive stars and the subsequent birth of neutron stars. In this sense, these telescopes serve as cosmic hunters, scanning the heavens for the telltale signs of these explosions to confirm the presence of these enigmatic stellar objects. So, why is the detection of neutron stars considered so important? The answer is found in the wealth of information they carry about the underlying physics of our universe. Every neutron star we find tells us a new story about the life cycle of stars and the behavior of matter under the most extreme pressures imaginable. By analyzing the properties of these objects, scientists can rigorously test our theories of gravity, relativity, and nuclear physics, helping to unravel some of the deepest mysteries of the cosmos. However, astronomers face immense difficulties in their search for these objects. The sheer vastness of space, combined with the incredible distances to these stars, makes their detection a monumental challenge. It is a pursuit that constantly pushes the boundaries of our technology and our ingenuity as we attempt to find these faint, hidden jewels scattered throughout the cosmos. To infer the presence of neutron stars, astronomers often have to be creative, relying on indirect methods. The search is akin to finding a needle in a haystack, where every piece of data is vital, and even a minor clue can spark major breakthroughs. As our technology has advanced, so too has our capacity to find and analyze these objects. Powerful instruments like the Hubble Space Telescope and the more recent James Webb Space Observatory grant us access to observe the cosmos in wavelengths we couldn't see before, giving us an unprecedented toolkit for studying these enigmatic entities. The effort to detect neutron stars has also been significantly bolstered by international cooperation. When observatories across the globe work together, scientists can pool their data and resources, leading to a much more thorough understanding of these cosmic events. This collaborative effort resembles a team of detectives solving a highly complex case, with each member bringing their unique skills and expertise to the table. In this grand quest of discovery, astronomers are doing more than just looking for neutron stars. They are actively deciphering the fundamental secrets of the cosmos. Every neutron star we identify serves as a portal into the universe's history, acting as a profound reminder that the cosmos is brimming with wonder and surprises. As our comprehension of these remarkable bodies deepens, we move closer to resolving foundational questions about the very nature of matter, energy, and existence itself. The search for neutron stars is, without a doubt, a thrilling frontier in astrophysics, filled with both immense challenges and incredible rewards. It's a journey that reveals as much about our place in the universe as it does about the stars themselves. A supernova is among the most breathtaking phenomena in the entire universe. But have you ever considered what follows such a cataclysmic explosion? Amidst the aftermath and chaos, a neutron star can form, a remnant so incredibly dense that it challenges our deepest understanding of physics. Today, I want to delve into the fascinating relationship between supernovae and neutron stars, a link that is absolutely critical to grasping how these mysterious cosmic objects come into being. Supernovae are essentially cosmic fireworks that signal the end of a massive star's life. But what exactly pushes a star toward such a dramatic end? When a star uses up all its nuclear fuel, it loses the ability to fight against the relentless pull of its own gravity. You can picture a balanced scale. If the weight on one side suddenly vanishes, the other side crashes down. For a star, this means its internal pressure can no longer support its immense weight, causing it to collapse in a spectacular burst of energy. Throughout this collapse, the star's outer layers are hurled violently into the surrounding space. This explosion is not just a stunning spectacle, it's also fundamental to the creation of the heavier elements that go on to define our universe. The very atoms of carbon, oxygen, and other elements necessary for life as we know it are forged within the fiery hearts of these cosmic detonations. But what truly captures our interest is what is left behind, the neutron star. Once the explosive fury of the supernova fades, an extraordinarily dense core is all that remains. Here, gravity crushes matter with such overwhelming force that electrons and protons are forced to merge, forming neutrons. This transformation is like compressing a vast collection of sponges into a tiny, solid ball. A neutron star can pack more mass than our own sun into a volume no larger than a city, and it is within this extreme compression that the true puzzle of these stars begins. However, the link between supernovae and neutron stars continues long after their formation. Did you know that the energy unleashed by a supernova can be so immense that the explosion is visible from billions of light years away? This incredible burst of energy doesn't just light up the cosmos, it also gives us a chance to investigate what remains. Astronomers study the light and gravitational waves produced by these events to gather clues about the properties of the resulting neutron stars. By examining both supernovae and the neutron stars they create, scientists can uncover details about the evolution of galaxies and the origins of chemical elements. These stellar remnants become natural laboratories where we can witness the laws of physics operating under conditions so extreme they are impossible to replicate here on Earth. Additionally, the supernovae that give birth to neutron stars are responsible for scattering essential matter across the cosmos, enriching interstellar gas and dust, and setting the stage for the formation of new stars and planets. Yet, not every star that goes supernova leaves behind a neutron star. Depending on their initial mass, some stars are destined to collapse further into black holes. This fact introduces a compelling question. What decides whether a dying star becomes a neutron star or a black hole? The answer is found in the precise amount of mass and pressure left after the explosion. Just a little more mass can completely alter the star's ultimate fate. As our knowledge of neutron stars grows, it's vital to recognize that they are far more than just the leftovers of stellar explosions. They are silent witnesses to the universe's long history, providing us a glimpse into events that took place billions of years ago. By studying them, we can begin to unravel some of the most profound mysteries of the cosmos. When you see a supernova, you're not just observing an explosion. You're watching a fundamental cosmic process that has sculpted our universe and our own existence within it. Born from the cataclysmic explosions of supernovae, neutron stars are the remnants that help us comprehend our position in this immense and amazing cosmos. These celestial objects serve as a constant reminder of the universe's intricacy and beauty, compelling you to peer beyond the visible spectrum, challenge your own assumptions, and stand in awe of the phenomena unfolding in the deepest reaches of space.
Every neutron star represents a story of profound transformation, an ongoing chapter in the grand narrative of the universe. So, the next time your eyes drift across the night sky, I want you to consider the violent stellar blasts that gave birth to the light you see. It's important to remember that each supernova contains a dual story of creation and destruction, a cycle of matter and energy that binds us all together within this vast cosmic tapestry. Neutron stars truly embody the magic of the cosmos, and their study is an open invitation to keep venturing into the unknown. This brings us to a fundamental question. What part do these objects play in our comprehension of the universe? When you think about space, your mind likely conjures images of radiant galaxies, far-off planets, or even enigmatic black holes. Yet, it's these unbelievably dense objects that are among the most critical pieces in the cosmological puzzle. These stars are not just captivating subjects on their own. Investigating them allows us to unlock some of the most profound secrets of the universe. A central question is how exactly a neutron star can yield information about cosmic evolution. The answer is found in its function as a natural laboratory for physics at its most extreme. When two of these stars collide, they unleash such a staggering amount of energy that it generates detectable gravitational waves, which ripple through space, telling us the story of their violent origin. Another aspect that fascinates scientists is the potential connection between neutron stars and dark energy. This mysterious force is thought to be responsible for the accelerating expansion of our universe. And while we don't yet fully grasp its nature, neutron stars might hold some of the answers. By studying their behavior and interactions, we could uncover vital clues about what this enigmatic energy truly is. I encourage you to imagine a neutron star as a lone beacon shining in the vast cosmic ocean. By analyzing its light and the gravitational waves it emits, scientists can map out the structure and trace the evolution of the universe. Observing how these stars behave under various conditions, for instance, provides critical insights into the formation of galaxies and the arrangement of matter throughout space. And what about nucleosynthesis? This term describes the process that forges the heaviest elements in the cosmos. Neutron star collisions are the cosmic furnaces where elements such as gold and platinum are created. In a way, every time you admire a piece of sparkling jewelry, you could be looking at the ancient legacy of these incredible celestial bodies, as these elements are born from their explosive encounters. Studying neutron stars is also vital for understanding dark matter, the elusive substance that constitutes the majority of the universe's mass yet remains invisible to us. By observing how neutron stars interact with the matter we can see, astrophysicists can deduce the properties of dark matter and clarify its crucial role in shaping the universe's structure. As our research progresses, these objects are proving to be genuine cosmic detectives, silently recording universal history for us to decipher. Their significance also extends directly to the field of cosmology. By mapping the distribution of neutron stars across the cosmos, we can gather data on the universe's expansion and the formation of its largest structures. This information helps us piece together how the universe has developed from its very inception to the state we observe today. One of the most thrilling aspects is how neutron stars hint at the absolute limits of physics as we know it. The conditions inside them are so extreme that they actively challenge our established theories, making them perfect natural laboratories for testing and questioning fundamental physical laws. If you could replicate those conditions here on Earth, the answers we'd find could completely revolutionize our knowledge of matter and the basic forces of nature. The link between neutron stars and gravity is an equally captivating subject. Their immense gravitational pull doesn't just act on their own matter. It profoundly warps the fabric of space and time surrounding them. This phenomenon compels us to rethink our entire conception of time and space, potentially opening the door to entirely new theories in physics. As our technology improves, so does our capacity to investigate these distant stars. Modern telescopes and sophisticated gravitational wave detectors permit us to explore the universe in ways that were simply unimaginable in the past. Every fresh discovery about neutron stars provides an updated and more refined perspective on cosmic history and our own place within it. When you reflect on the cosmological importance of neutron stars, it's vital to remember that every step forward in this field invariably uncovers a new set of questions. What other secrets can we learn about the universe by studying these objects? What deeper mysteries are still waiting to be revealed? This search for answers is a continuous journey that pushes us to explore the very boundaries of the cosmos. Ultimately, the study of neutron stars not only enhances our understanding of the universe, but also prompts us to contemplate our own existence. By learning more about the cosmos, you come closer to understanding your unique place in it and the incredible history that connects you to everything. The adventure of comprehending the universe is truly just beginning, and neutron stars stand as some of our most intriguing guides on this cosmic voyage. It's no surprise that neutron stars have captivated so many people, thanks not only to their stunning appearance and unbelievable density, but also to their portrayal in popular culture. What is it about such a compact celestial object that has fueled countless stories and theories? To find the answer, we need to look at how neutron stars have been woven into our shared stories, from movies to novels and everything in between. In science fiction cinema, you'll often see neutron stars depicted as enigmatic cosmic lighthouses, broadcasting radiation and energy across the immense void of space. While these representations tend to dramatize their features, there is a core of truth to them. Neutron stars are indeed unfathomably dense and possess gravitational fields of immense power, rendering them exceptionally hostile and perilous environments. However, this inherent danger has never deterred screenwriters and authors from using them as the backdrop for thrilling intergalactic sagas. In numerous narratives, neutron stars provide the ideal setting for grand conflicts. Can you picture a space battle where starships must navigate the intense radiation of a pulsar, which is a rapidly spinning neutron star? The concept is not just exciting, it captures the fascination with the risk and uncertainty these cosmic phenomena represent. Stories that feature neutron stars are frequently steeped in suspense, which makes them a perfect ingredient for science fiction. A prime example can be found in the film Interstellar, where the characters must contend with the bizarre effects of extreme gravity near a black hole. Although the movie isn't solely about neutron stars, its visualization of gravitational forces certainly piques curiosity about these dense objects and makes you wonder what would happen if you ever ventured too close. Neutron stars also make appearances in literature, where their incredible density and extreme properties serve as powerful metaphors for exploring the complexities of the human condition. It's remarkable how these minuscule celestial bodies can have such a major influence on the way we perceive the cosmos.
Some writers have used the neutron star to symbolize the unreachable, mirroring the immense challenges we encounter in our own lives. Of course, not every portrayal you see is scientifically grounded. In many instances, neutron stars are presented as almost legendary entities, possessing abilities that seem nearly supernatural. But can they actually have superpowers? The reality is that their power is rooted in their extraordinary physics, not in some fantastical capability. This kind of portrayal can unfortunately lead to misconceptions about what they truly are and their actual role in the universe. Even the world of video games has adopted the concept of neutron stars. In titles such as No Man's Sky, players get to explore star systems that contain these objects. Just imagine journeying through the digital heavens of a fictional universe and encountering neutron stars on your travels. This idea is not only thrilling, but also guides players on an educational path through astrophysics, though presented in a more light-hearted manner. Beyond entertainment, neutron stars stand as symbols in our ongoing quest for knowledge. In documentaries and popular science shows, they are often showcased as gateways to understanding the universe's deepest secrets. Their importance to scientists lies in their ability to help answer fundamental questions about the nature of matter and the behavior of gravity under the most extreme conditions imaginable, sparking a growing fascination with astrophysics among the public. It's truly intriguing to see how, regardless of the different ways they are depicted, a common thread of fascination with the unknown persists. With their crushing density and powerful magnetic fields, neutron stars embody the very frontiers of human understanding. This interplay between scientific fact and creative fiction has drawn more people to science, even if their initial understanding is sometimes incomplete. While the depictions in popular culture are certainly entertaining, it's crucial to remember the science that underpins them. Neutron stars are more than mere plot devices. They represent a vibrant field of research that helps us decode the mysteries of our universe. The curiosity they inspire is a powerful force, and the journey of exploration and learning it drives is just getting started. Ultimately, popular culture doesn't just mirror our interest in neutron stars. It actively amplifies it, fostering a feedback loop of curiosity and discovery. As new films, books, and video games continue to inspire the next generation, the study of these enigmatic celestial bodies is sure to remain a captivating field. Who can say what new tales will be born from the incredible reality of neutron stars in the years to come? Did you know that throughout history, these dense and fascinating entities known as neutron stars have been the focus of numerous myths and misunderstandings? They are frequently mistaken for black holes or assigned abilities that border on the supernatural. But what is a neutron star really? And why does so much mystery seem to surround it? Let's clear up some of the most widespread misconceptions about these incredible stellar remnants. First, let's address the topic of their size. A lot of people assume neutron stars are massive in scale, but the truth is, they are extraordinarily compact. To give you some perspective, a neutron star might only be as large as a city, yet it can contain a mass comparable to our own sun. Just try to imagine squeezing all of that material into such a tiny volume. It's a truly mind-boggling reality. Another common myth suggests that neutron stars are inert objects, little more than dead rocks drifting through space. In reality, these stars are incredibly dynamic. Some of them spin at breathtaking velocities, rotating up to thousands of times every second. This rapid spin not only makes them active, but also generates remarkable phenomena like pulsars, which emit beams of radiation that we can detect from Earth, proving they are anything but boring. Now let's discuss their gravity. Most of you understand that gravity is the force that plants our feet firmly on the ground. But are you aware that the gravitational pull on the surface of a neutron star is millions of times stronger than it is here on Earth? It's a force so immense that it challenges the very limits of our imagination. This implies that any object attempting to break free from its gravitational grasp would be ensnared forever. The notion that you could leap away and never land is genuinely unsettling. Yet it describes the fate of anything that strays too close to a neutron star. A prevalent myth also suggests that all neutron stars are destined to become black holes, but this isn't quite the case. While that is the ultimate end for some, a great many will persist as neutron stars for millions or even billions of years, which is where the concepts can become muddled, leading to confusion between these celestial bodies. The misunderstanding doesn't stop there. It also applies to their magnetic fields. It's a common mistake to think of neutron stars as nothing more than powerful gravitational sources, when in fact, they generate magnetic fields of unimaginable strength. These fields are capable of being trillions of times more powerful than the ones surrounding our own planet. Just try to comprehend the influence of a colossal magnet that can manipulate matter across immense cosmic distances. Can you even begin to imagine the repercussions of such a force in space? Another frequently misunderstood characteristic of neutron stars is their rotation. You might assume their incredibly fast spin rates would make them highly unstable, but the opposite is true. This rapid rotation is what actually keeps them stable. The principle is much like a figure skater who spins faster by drawing their arms inward toward their body. The physics that dictate their spin are truly captivating and serve as a beautiful demonstration of the universe's mechanics in motion. Some might dismiss neutron stars as purely theoretical constructs, but the reality is that they have been actively observed and analyzed. The very first pulsar, which is a type of neutron star, was identified back in 1967, and astronomers have located countless more in the decades since. This ongoing discovery proves that our knowledge of these objects is constantly expanding and being refined. In popular culture, these stellar remnants don't appear as often as other cosmic phenomena, but they have made their way into various films and novels, where their portrayal is often inaccurate, further contributing to public confusion. Perhaps you've wondered what purpose neutron stars serve in the grand scheme of the universe. While they may seem incredibly remote and disconnected from our lives, their study offers profound insights into the laws of physics, the nature of gravity, and the overall evolution of the cosmos. Every new piece of information we gather about them moves us closer to a complete picture of how everything came to be and how it all operates. Rather than just being the final chapter for massive stars, they represent a pivotal stage in stellar evolution that tells us a great deal about the life and death of stars. It's often said that knowledge is power, a sentiment that is especially true when it comes to understanding neutron stars. By clearing up the myths surrounding them, we not only gain a more accurate view of these cosmic objects, but also deepen our appreciation for the sheer diversity and complexity of our universe. Recent years have seen an incredible acceleration in neutron star research, with each new finding bringing us nearer to solving the universe's deepest puzzles. How can an object so incredibly small and dense hold so much information about fundamental physics? Answering that is a central goal of modern scientific inquiry. Scientists are employing cutting-edge telescopes and observatories to examine these captivating objects, uncovering details once considered impossible to obtain. As an example, we have successfully detected radio waves from pulsars located thousands of light-years away. This achievement has provided us with a much clearer understanding of their behavior and fundamental properties, demonstrating the power of our modern instruments. Among the most thrilling recent breakthroughs is the detection of collisions between neutron stars, which produce gravitational waves, a phenomenon that was first directly observed in 2015. These waves are essentially ripples in the fabric of spacetime, much like the concentric circles that form when a stone is dropped into a pond. By studying them, we can learn the stories of the most cataclysmic events occurring across the cosmos. A collision between neutron stars releases a colossal amount of energy and matter, including many of the universe's heavy elements. This raises a fascinating possibility. Could the gold and platinum on our own planet have been forged in the crucible of these violent cosmic mergers? Modern technology, including telescopes that can see across the entire electromagnetic spectrum from visible light to gamma rays, has allowed astronomers to capture these events in unprecedented detail. They can now observe kilonova explosions, which are the brilliant flashes that occur when two neutron stars merge, opening a new frontier in astrophysics. The investigation of neutron stars has also propelled our understanding of matter under the most extreme conditions imaginable. Picture the entire mass of a giant star being crushed into a sphere no larger than a small city. Within the core of a neutron star, the pressure becomes so immense that protons and electrons are forced to merge, forming neutrons. This has led scientists to develop new theories about exotic forms of matter, like strange matter, where particles such as quarks and gluons might exist in states we cannot replicate or observe under any normal circumstances. So, what causes the regular pulses of light that some neutron stars emit? These signals are a direct consequence of the star's incredibly fast rotation, which can reach thousands of revolutions per second. Furthermore, ongoing research has revealed that these pulsars don't just radiate light. They also emit energy in other forms, such as powerful beams of X-rays, painting a more complete picture of these extraordinary cosmic lighthouses. Have you ever considered what lies ahead in the study of neutron stars? These captivating celestial bodies have sparked the imagination of both scientists and the public, yet their exploration has only just begun. Within the immense and enigmatic expanse of the universe, neutron stars serve as guiding lights, illuminating the most profound mysteries of physics and astrophysics. First and foremost, technology is progressing at a phenomenal rate. Instruments and detectors that were once confined to the realm of science fiction are undergoing constant enhancement. Because of these improvements, astronomers are now able to witness phenomena that were previously hidden from view, allowing them to observe the light from neutron stars billions of light-years away, or detect gravitational waves from their cataclysmic mergers. One of the most thrilling prospects in future neutron star research is the potential to find new and bizarre states of matter. Deep inside these stellar remnants, matter behaves in ways that challenge our everyday intuition. Imagine if we could not only observe, but also replicate these extreme conditions in laboratories here on Earth, a direction science is actively pursuing with new experimental designs that could transform our knowledge of physics. As our exploration of the cosmos continues, fresh theories are constantly taking shape. It's possible that neutron stars hold the answers to understanding cosmic puzzles like dark energy and dark matter. Scientists find themselves at a pivotal point where each discovery could lead to a host of new inquiries, and this self-perpetuating cycle of discovery is precisely what makes studying neutron stars so compelling. The development of specialized telescopes for detecting emissions from these stars has given us a much clearer understanding of their properties and behavior. Furthermore, Research into neutron stars has provided crucial insights into the history of the cosmos. Scientists have found that these objects function as a type of cosmic signpost. By examining their distribution and interaction with their surroundings, we gain knowledge about the universe's expansion and the formation of galaxies. Isn't it remarkable that an object so small and distant can offer clues about the origins of everything we know? Another fascinating area of modern research involves the role neutron stars play in cosmology. As scientists analyze the light and gravitational waves emanating from these stars, they are piecing together how they fit into the grand cosmic puzzle, helping us refine our models of dark matter and dark energy, two of the most significant enigmas in contemporary physics. So, the next time you gaze up at the night sky, consider that those tiny points of light could hold the keys to deciphering the universe's greatest secrets. Progress, however, isn't confined to observation alone. Computer simulations are now indispensable in neutron star research, allowing scientists to model the extreme conditions within them and predict their behavior in different situations, providing data that would be otherwise unattainable. This capability is critical, since we cannot directly witness every process unfolding across the cosmos. These powerful simulations function like virtual laboratories, where we can explore what happens during the collision of two neutron stars, an event that can unleash more energy than our sun will generate in its entire lifespan, or peer into the very core of a star itself. As our technological capacity for gathering and analyzing data improves, so does the power of collaboration. The scientific community is united by a common desire to share and disseminate knowledge, with international partnerships between observatories and research centers leading to an unparalleled exchange of information. This collective effort allows scientists to combine their findings and construct a more unified understanding of these celestial mysteries. Pulsars, which are rapidly spinning neutron stars, offer a particularly promising avenue for investigation within this field. Each new pulsar discovered opens up a fresh spectrum of possibilities for probing the nature of gravity and time. The incredibly regular pulses of their signals can be utilized as cosmic clocks, providing you with a unique tool for testing fundamental physics. The study of neutron stars is a field in constant flux, with new questions emerging every day. What further secrets about physics can these objects reveal, and how might they reshape our entire perception of the universe? The possibilities are boundless, and researchers are committed to continuing this exploration, knowing that with every new discovery, we move closer to understanding not just neutron stars, but the very structure of reality. In this scientific journey, it's vital to recognize that every solution often uncovers new puzzles. It is human curiosity that compels us to push further and venture into unknown territories. Looking ahead, the investigation of neutron stars will undoubtedly continue to light our way toward a more profound comprehension of our place in the cosmos, with each breakthrough representing another step in solving the enigmas that await. This capability might grant scientists the power to chart cosmic distances with unparalleled accuracy. One can only imagine the profound secrets that these celestial flashes of light are waiting to unveil. Gravitational waves, as we've discussed, represent another thrilling frontier. Observing these ripples in spacetime from neutron stars has already transformed astrophysics, and with advancing technology, we will soon capture fainter and more remote cosmic events, which promises to reshape our view of the cosmos itself. These gravitational waves act as echoes from the deep past, narrating tales of cataclysmic events across the universe. Looking ahead, education and science outreach will be indispensable to the study of neutron stars.
A growing public fascination with science is introducing fresh perspectives and new voices into the conversation. Since curiosity tends to spread, an increasing number of young minds are being motivated to investigate the cosmos, a trend that enriches astrophysics while also cultivating a universal sense of wonder that is vital for our collective future. The path forward in neutron star research could also be intimately tied to our very existence. By investigating these extraordinary objects, you begin to grasp your own place within the grand scale of the universe, forcing us to ask how this new knowledge might alter the way we see the world and our own lives.
The quest for life beyond Earth might also be shaped by what we learn about neutron stars. It prompts the question, could the hostile environments surrounding them actually harbor previously unimagined forms of existence? Though it sounds like science fiction, the field of astrobiology is continually pushing boundaries. The insights we gather from these dense stars could very well direct our search for life in distant parts of the galaxy. Every fresh discovery inevitably leads to a new set of questions. You're left to wonder what puzzles are still waiting to be solved, and what the next major advance in neutron star research will be. Ultimately, it is our limitless human curiosity and the deep-seated urge to comprehend the unknown that propels scientific progress ever onward.
To sum up, the future of studying neutron stars is incredibly promising and brimming with potential. Driven by advancing technology, global scientific partnerships, and a rising public fascination, we are standing at the threshold of a new era in cosmic exploration. I encourage you to keep looking up, as neutron stars are certain to continue astonishing us and pushing the limits of our cosmic knowledge. Our great adventure is only getting started. In the immense sea of cosmic mysteries, neutron stars act as lighthouses, lighting the way for us to comprehend our position in its infinite depths. This very inquiry encourages a deep contemplation of our own existence and the fundamental fabric of the universe.
When we observe neutron stars, our investigation goes beyond a simple astronomical spectacle. We are delving into profound questions about the nature of time, space, and matter itself. Every new neutron star identified serves as a portal to the distant past, as these objects are the collapsed cores left behind by massive stars that died in cataclysmic supernova explosions. Analyzing them allows us to piece together the life cycle of stars and, by extension, the origin of the very elements that constitute everything you know. It's truly incredible to consider that each atom within you might have originated inside a star that lived and died eons ago. The sheer density of neutron stars raises some fascinating questions for us to ponder. Just try to picture a single teaspoon of material from a neutron star, weighing as much as an elephant. This level of compression forces us to rethink our entire conception of gravity and space. Our everyday experience defines matter as something tangible, but these celestial objects introduce you to a state of matter that completely subverts your most fundamental intuitions. Another feature that inspires deep thought is their magnetism. Neutron stars produce magnetic fields that are billions of times more powerful than Earth's, which leads you to contemplate how radically different your life would be in a reality governed by such immense magnetic forces. The unbelievably fast rotation of certain neutron stars also provides food for thought. You might ask if time itself could function differently in such extreme environments, and the answer is a definitive yes. The theory of relativity explains that time is not a fixed constant. Rather, it's a fluid variable that can be warped by gravity and velocity. This idea compels you to reconsider your own daily perception of time and question how well you genuinely comprehend its true essence.
As we explore the phenomenon of gravitational waves, we discover what is essentially a method of cosmic communication. Each detection delivers a message about a spectacular event from the distant universe, drawing us nearer to unlocking cosmic secrets and reminding us that we are part of something much greater.
The significance of neutron stars extends beyond physics, as they also shape our comprehension of cosmic origins. By studying their formation and evolution, we contribute to building the story of the universe's history, revealing connections between these objects, the Big Bang, and cosmic expansion. While exploring these subjects, you are also compelled to contemplate the fragility of your own existence. The cosmos is an immense and frequently hostile environment, and neutron stars serve as a stark reminder that life is an exceptionally rare and valuable occurrence.
Have you ever found yourself gazing into the night sky, wondering about the secrets held by the stars? As we've journeyed through the incredible science of neutron stars, we've touched upon their creation, their makeup, and their cosmic influence. But the real question is what this knowledge means for you and me, inhabitants of a tiny outpost in the universe. Our investigation of these celestial marvels ultimately leads us to reflect on our own connection to them and what they reveal about our place in this immense cosmos. While neutron stars might appear impossibly distant, they serve as powerful mirrors, reflecting the grand history of the universe. By analyzing their characteristics, we unlock the secrets of matter and energy, the very building blocks of everything we perceive. It's a breathtaking realization that by examining a neutron star, you are fundamentally probing the same elements that constitute your own being. It's all too easy to forget that the atoms composing life on Earth were originally forged inside ancient stars.
These objects remind us that matter can exist in states so extreme they defy our everyday comprehension. For instance, what if I told you that a mere teaspoon of a neutron star's substance has the same mass as 1 million elephants? The thought is staggering, yet it also serves as an invitation to investigate our own cosmic origins. The gravitational pull on these stars is equally mind-bending. On their surface, the force is so immense it would obliterate you in a fraction of a second. This terrifying power, however, offers a profound lesson on the intricate and vast scale at which the universe operates, where gravity dictates the destiny of stars and even warps time itself. And what can be said of magnetism? Neutron stars generate magnetic fields millions of times more powerful than anything achievable on Earth. Beyond being a scientific curiosity, these fields serve as a humbling reminder that forces exist in the cosmos which we have only begun to comprehend. The swift rotation of these stars, which causes many to become pulsars, offers a distinct window into the fabric of space and time. You can picture a lighthouse spinning in the cosmic dark, its beams of light guiding us across an endless ocean of knowledge, with each pulse acting as a cosmic heartbeat, signifying a universe that is dynamic and perpetually in motion. When we study the cosmological role of neutron stars, you can begin to see how these extreme objects are critical to understanding the universe's evolution. They hold clues to how galaxies took shape and what might have occurred in the moments following the Big Bang. The life and death of these stellar remnants are directly tied to the answers we seek about the origins of everything around us. Every new piece of data gathered in this field moves us one step closer to grasping the full story of our cosmic beginnings. Yet, the insights we gain are not confined to the realm of science. Neutron stars have ignited human imagination, leaving their imprint on everything from literature to film. And these cultural portrayals demonstrate how scientific concepts can inspire powerful and amazing narratives. As our research capabilities advance, revelations about neutron stars continue to astound scientists, with each discovery paving the way for even more fascinating questions. This endless cycle speaks to our insatiable human curiosity and affirms that the study of these objects is a testament to our unending search for knowledge. Ultimately, reflecting on all we have learned makes it apparent that neutron stars are far more than simple astronomical curiosities. They are lighthouses of knowledge, illuminating our comprehension of the universe and our unique position within it. Their study reveals that we are an integral part of something immeasurably larger, a cosmos overflowing with mystery and wonder. We are faced with the reality that, for all our technology and ambition, we are small. Yet this perspective encourages us to consider our greater purpose. In the end, neutron stars teach us that everything in the universe is interconnected. Each star, every planet, and all life are woven into a single cosmic tapestry. And by studying these objects, you are, in a way, exploring your own history. The real beauty is found not just in the answers, but in the journey itself, in the curiosity that drives us and the profound connection we feel to the cosmos. So the next time you look up at the stars on a clear night, remember that every point of light may be a story waiting to be told, inviting you to continue the exploration. As our discussion concludes, it's vital for you to recognize that comprehending the universe extends beyond a purely scientific pursuit. It is an intensely personal voyage for each of us. You have a part to play in this magnificent exploration, whether your contribution lies in academic research, in educating others, or simply in maintaining a profound curiosity. Therefore, I encourage you to continue looking up at the stars and pondering the new knowledge they hold. For the revelations that await are certain to be as extraordinary as the cosmos itself.